Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're embarking on a peaceful journey to the smallest planet in our solar system, Mercury. This mysterious world, named after the swift Roman messenger god, holds secrets that have puzzled astronomers for centuries. We'll explore its scorched surface, its surprisingly complex interior, its wispy atmosphere that barely exists, and the strange way it dances around the sun. We'll discover why this tiny planet has such an enormous iron heart, how it survives being battered by solar radiation, and what ancient volcanic plains tell us about its violent past. From the towering cliffs that dwarf anything on Earth to the ice hiding in shadows that never see sunlight, Mercury is a world of extremes and contradictions. Before we begin, if you enjoy these types of videos, I'd really appreciate it if you'd give this a thumbs up and consider subscribing to the channel. It helps me continue creating these cosmic bedtime stories for all of you. I'm also curious, where are you watching from right now, and what time is it where you are? Drop a comment below. I love hearing from fellow night owls and space enthusiasts around the world. Let's dive in. Mercury sits just 36 million miles from the Sun, making it the innermost planet in our solar system. To put that in perspective, if Earth were a basketball sitting 100 feet from a bonfire, Mercury would be a golf ball placed just 39 feet away. This proximity to our star defines everything about Mercury's character. The planet completes one orbit around the Sun every 88 Earth days, moving through space at a blistering speed of nearly 105,000 miles per hour. Ancient astronomers noticed how quickly Mercury appeared to move across the sky, which is precisely why they named it after the fastest of the Roman gods. Despite being the closest planet to the Sun, Mercury isn't actually the hottest planet in our solar system. That title belongs to Venus, whose thick atmosphere traps heat like a blanket. Mercury, by contrast, has almost no atmosphere to speak of, which creates the most extreme temperature swings in the solar system. During the day, when the sun beats down on Mercury's surface, temperatures can soar to 800 degrees Fahrenheit, hot enough to melt lead. But without an atmosphere to hold that heat, nighttime temperatures plummet to minus 290 degrees Fahrenheit. That's a temperature difference of over 1,000 degrees, like going from the inside of an oven to far colder than any winter on Earth, all in one day. Mercury is small, only slightly larger than Earth's moon. With a diameter of just 3,030 miles, you could fit about 18 Mercuries inside Earth. If you could stand on Mercury's surface, you'd weigh only about 38% of what you weigh on Earth. A person weighing 150 pounds on Earth would weigh just 57 pounds on Mercury. This low gravity is a consequence of Mercury's small size and, as we'll discover later, its unusual composition. The planet spins very slowly on its axis, taking 59 Earth days to complete one rotation. This slow spin, combined with its fast orbit, creates a peculiar situation. A single day on Mercury, from one sunrise to the next, actually lasts 176 Earth days. That means a Mercury year is only 88 days long, but a Mercury day is 176 days long. In other words, 2 Mercury years pass in the time it takes for one complete day and night cycle. Mercury has been known to humanity since ancient times, visible to the naked eye as a bright point of light that appeared near the horizon just after sunset or just before sunrise. The ancient Sumerians wrote about Mercury as early as the 3rd millennium BCE, calling it Nabu after their god of wisdom and writing. The ancient Greeks actually thought Mercury was 2 different celestial bodies, calling the morning appearance Apollo and the evening appearance Hermes. It wasn't until the time of Pythagoras, around the 5th century BCE, that Greek astronomers realized these were observations of the same wandering star. The challenge of observing Mercury has always been its proximity to the Sun. The planet never strays far from our star in the sky, appearing only during twilight hours when the sky is still somewhat bright. This makes detailed observation difficult. Ancient astronomers had to catch Mercury during those brief windows when it reached its greatest angular distance from the Sun, an event astronomers call greatest elongation. Even then, they were looking through thick layers of Earth's atmosphere near the horizon, which distorts and blurs the image. The invention of the telescope in the early 17th century promised new insights into Mercury's nature. Galileo Galilei observed Mercury through his primitive telescope beginning in 1610, though the planet's small size and proximity to the Sun made detailed study nearly impossible. He was able to observe that Mercury went through phases like our Moon, appearing as a crescent or gibbous shape depending on its position relative to Earth and the Sun. This observation was crucial evidence supporting the Copernican model of the solar system, which placed the Sun at the center rather than Earth. In the 1630s, Giovanni Zuppi made the first telescopic observations that confirmed Mercury showed phases, definitively proving that Mercury orbited the Sun and not Earth. Throughout the 17th and 18th centuries, astronomers continued making incremental improvements in their understanding of Mercury. They refined measurements of its orbital period and began attempting to map surface features, though these early maps were largely speculative and inaccurate due to the difficulty of observation. The 19th century brought a mystery that would puzzle astronomers for decades. In 1859, a French mathematician discovered that Mercury's orbit didn't behave quite as Newton's laws of gravity predicted. The point of Mercury's closest approach to the Sun, called perihelion, slowly shifted position over time. This shift, called perihelion precession, occurs for all planets, but Mercury's precession was faster than could be explained by the gravitational influence of other planets. It was calculated that Mercury's perihelion advanced by about 43 arc-seconds per century more than Newton's theory predicted. This tiny discrepancy might seem insignificant, but in science, when observations don't match theory, it usually means something interesting is going on. Some astronomers proposed the existence of another planet, which they named Vulcan, orbiting even closer to the Sun than Mercury. Observers even claim to have spotted this hypothetical planet during solar eclipses. However, no such planet was ever confirmed to exist. The mystery of Mercury's orbit remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's new understanding of gravity, which described it not as a force but as a curvature of spacetime, perfectly predicted Mercury's orbital precession. The intense gravitational field near the Sun warped spacetime enough to cause Mercury's orbit to shift in exactly the way astronomers observed. This was one of the first major confirmations of general relativity and showed that Mercury, despite being small, was helping us understand the fundamental nature of the universe. Sometimes the smallest things reveal the biggest truths. When we look at Mercury through a telescope, even a powerful one, we see a world that resembles our Moon, covered in craters and lacking the obvious features like clouds or polar caps that mark other planets. But Mercury's surface tells a story billions of years old, written in impact scars, volcanic plains, and mysterious cliffs that stretch for hundreds of miles. The most obvious features on Mercury are its impact craters, created when asteroids and comets slammed into the surface. These craters range from tiny bowls just a few feet across to enormous basins hundreds of miles wide. The largest confirmed impact structure on Mercury is the Caloris Basin, a massive scar measuring roughly 960 miles across. To visualize this, imagine a crater so large that if it were placed over the eastern United States, it would stretch from New York to South Carolina. The impact that created Caloris was so powerful that it sent shock waves through the entire planet, creating strange, jumbled terrain on the opposite side of Mercury. When a large asteroid strikes a planet at cosmic speeds, typically tens of thousands of miles per hour, the impact releases energy equivalent to billions of nuclear bombs. The rock at the impact site instantly vaporizes, creating a blast wave that excavates a deep crater. On Mercury, many craters have bright rays extending outward from them, made of fresh material thrown out during the impact. These rays can stretch for hundreds of miles, like splash marks frozen in stone. Over time, exposure to solar radiation and micrometeorite impacts slowly darkens these rays, so bright rays indicate relatively young craters. Between the craters lie smooth plains that cover about 40% of Mercury's surface. For many years, scientists debated whether these plains were formed by ancient lava flows or by material ejected from impacts. Data from spacecraft missions has confirmed that these are indeed volcanic plains, similar to the Dark Maria on our moon. Billions of years ago, Mercury was volcanically active, with lava seeping up through cracks in the crust and flooding low areas. These lava flows buried older craters and created the relatively smooth surfaces we see today. The most peculiar geological features on Mercury are its enormous cliffs, called lobate scarps. These scarps can be over a mile high and stretch for hundreds of miles across the surface. Discovery Rupees, one of the largest known scarps, is about 400 miles long. These cliffs were created as Mercury's interior cooled and contracted. Think of what happens to a grape as it dries into a raisin. The skin wrinkles and folds as the interior shrinks. Mercury did something similar, but instead of wrinkles, its solid crust cracked and thrust upward, creating these massive scarps. Scientists estimate that Mercury's radius has shrunk by about 4 to 7 miles since the planet formed 4.5 billion years ago. That might not sound like much for a planet 3,000 miles wide, but it represents an enormous amount of contraction. This shrinking continues today, making Mercury a tectonically active world. Recent high-resolution images have revealed small scarps that appear to cut through small craters, suggesting these scarps formed relatively recently, perhaps within the last 50 million years. Mercury's surface is also covered in a fine dust called regolith, created by billions of years of meteorite impacts. Each impact, no matter how small, chips away at the surface rocks, grinding them into progressively finer powder. This regolith is extremely dark, reflecting only about 11% of the sunlight that hits it. Mercury is actually one of the darkest terrestrial planets, despite being so close to the sun. For comparison, Earth's moon reflects about 12% of incoming sunlight, making it only slightly brighter than Mercury. If we could slice Mercury in half and look inside, we'd discover one of the most puzzling aspects of this small planet. Mercury has an enormous iron core that makes up about 61% of its volume. To understand how unusual this is, consider that Earth's iron core makes up only about 17% of its volume. If Earth had the same proportions as Mercury, our planet would be significantly smaller and much denser. Mercury is the second densest planet in the solar system, with only Earth being denser, and Earth's greater density is partly due to gravitational compression from its larger mass. Why does Mercury have such a disproportionately large core? This question has puzzled planetary scientists for decades, and several theories attempt to explain it. One possibility is that Mercury originally formed with more rocky material surrounding its core, but a catastrophic collision with another planet-sized body early in the solar system's history stripped away much of that rocky mantle, leaving the metal-rich core relatively exposed. This is similar to what scientists think happened to Earth when a Mars-sized body struck us, creating our moon. Another theory suggests that in the early solar system, when Mercury was still forming, the intense heat and solar wind from the young sun might have vaporized and blown away lighter rocky materials, leaving behind the heavier metallic elements that eventually formed Mercury's large core. Think of it like a cosmic winnowing process, where the sun's energy sorted materials by weight, allowing lighter elements to be pushed outward while heavier elements remained close in. A third possibility involves the chemistry of the early solar system. Different regions of the protoplanetary disk had different compositions, and the area where Mercury formed might have simply been richer in metallic elements. This would mean Mercury formed with its current proportions rather than losing material later. Each of these theories has evidence supporting it, and the truth might involve a combination of all three processes. Mercury's core is not entirely solid. Scientists believe it has a solid inner core surrounded by a liquid outer core, similar to Earth's structure. We know the outer core must be liquid because Mercury generates its own magnetic field, and the most common way to create a planetary magnetic field is through a dynamo effect in a liquid metallic core. As the planet rotates, the liquid iron in the core circulates, and these flowing electric currents create magnetic fields. However, Mercury's magnetic field is much weaker than Earth's, only about 1% as strong. This weak field still provides some protection from the solar wind, creating a small magnetosphere around the planet. The solar wind, a stream of charged particles flowing out from the sun, pushes against this magnetosphere, compressing it on the side facing the sun and stretching it into a tail on the night side, like a windsock in a breeze. Surrounding the core is a mantle made of silicate rocks, similar to the rock that makes up Earth's mantle but much thinner relative to the planet's size. This mantle is only about 260 miles thick, compared to Earth's mantle, which is about 1,800 miles thick. Above the mantle lies a crust estimated to be only 20 to 30 miles thick in most places. This thin crust is one reason why Mercury's ancient volcanic activity was able to bring lava to the surface relatively easily. Recent research suggests Mercury's core may be partially solid now, freezing from the inside out as the planet slowly cools. As liquid iron crystallizes onto the solid inner core, it releases heat and light elements that rise through the outer liquid core, driving the dynamo that creates Mercury's magnetic field. This process may have been going on for billions of years and could continue for billions more, though the magnetic field will likely continue to weaken as the core cools. When we think of a planetary atmosphere, we usually imagine something like Earth's thick blanket of air, or perhaps the crushing carbon dioxide atmosphere of Venus. Mercury's atmosphere, if we can even call it that, is nothing like these. It's so incredibly thin that scientists often call it an exosphere rather than an atmosphere. The entire exosphere contains only about 2,000 pounds of material. To put that in perspective, if you could gather all of Mercury's atmosphere and weigh it, it would weigh less than a small car. The atoms and molecules in Mercury's exosphere are so sparse that they rarely collide with each other. Instead, individual atoms follow ballistic trajectories, like tiny baseballs thrown upward, arcing through space before falling back to the surface under Mercury's weak gravity. The exosphere is constantly being stripped away by the solar wind and replenished by various processes we'll explore. An atom in Mercury's exosphere typically spends only about 3 hours aloft before either escaping to space or crashing back into the surface. So what is Mercury's exosphere made of? The composition is surprisingly varied and includes hydrogen, helium, oxygen, sodium, potassium, calcium, and magnesium. The proportions of these elements change over time and vary by location. Sodium and potassium are particularly interesting because they emit light at specific wavelengths that astronomers can detect from Earth. By observing this glow, scientists can study how Mercury's exosphere responds to changes in solar activity and the planet's position in its orbit. Where do these atoms come from? There are several sources. Some atoms, particularly hydrogen and helium, come directly from the solar wind. These light elements are constantly streaming away from the sun, and some get temporarily captured by Mercury's weak gravity. Other atoms are knocked off the surface by solar wind particles in a process called sputtering. Imagine tiny bullets hitting the surface and knocking off individual atoms. It's like using a sandblaster, but with charged particles instead of sand grains. Another source is photon-stimulated desorption, where intense ultraviolet light from the sun gives atoms on the surface enough energy to break free and leap into the exosphere. Additionally, micrometeorites constantly rain down on Mercury's surface. These impacts, though individually tiny, collectively vaporize surface material and loft atoms into the exosphere. It's been estimated that Mercury's surface receives about 3 times as many micrometeorite impacts as our Moon, due to Mercury's proximity to the Sun and the gravitational influence of the Sun focusing incoming material. Mercury's exosphere also interacts with the planet's magnetic field and the solar wind in complex ways. During magnetic storms on the Sun, the increased solar wind pressure can compress Mercury's magnetosphere, allowing more solar wind particles to reach the surface and increasing the rate of sputtering. This creates temporary enhancements in the exosphere, particularly on the day side of the planet. Sodium atoms, being relatively heavy, tend to accumulate in a tail extending away from the Sun, creating a faint comet-like feature that astronomers can sometimes detect from Earth. Temperature plays a crucial role in the behavior of Mercury's exosphere. On the scorching day side, where surface temperatures reach 800 degrees Fahrenheit, more atoms have enough thermal energy to escape from the surface. On the frigid night side, where temperatures plunge to minus 290 degrees, atoms tend to stick to the surface and freeze out. This creates a day-night asymmetry in the exosphere, with the day side having a much denser exosphere than the night side. The study of Mercury's exosphere helps scientists understand similar processes occurring on other airless bodies in the solar system, including our Moon, and provides insights into how planetary atmospheres evolve over time. Mercury represents an extreme case, where an atmosphere is continuously being lost and replenished, never reaching equilibrium, always changing. Mercury's orbit around the Sun is one of the most eccentric among the planets, meaning its path is noticeably elliptical rather than circular. At its closest approach to the Sun, called perihelion, Mercury comes within 29 million miles of our star. At its farthest point, called aphelion, Mercury reaches 43 million miles away. This means Mercury's distance from the Sun varies by about 14 million miles during each orbit, a difference of nearly 50%. This eccentric orbit has profound effects on Mercury's environment. When Mercury is at perihelion, it receives about 2.5 times more solar radiation than when it's at aphelion. Imagine the difference between standing near a campfire and then moving several feet away. The heat you feel drops dramatically with distance, and the same principle applies to Mercury. The intensity of sunlight, and therefore the temperature on Mercury's surface, varies significantly throughout the planet's 88-day year. The relationship between Mercury's rotation and its orbit is one of the strangest in the solar system. Mercury is tidally locked to the Sun, but not in the way our Moon is tidally locked to Earth. Our Moon always shows us the same face because it rotates once per orbit. Mercury, however, rotates 3 times for every 2 orbits it completes. This 3-to-2 ratio is called a spin-orbit resonance, and it means that some parts of Mercury experience very different conditions than others. Here's where things get interesting. Because of this 3-to-2 resonance, there are 2 locations on Mercury's equator, exactly opposite each other, that experience the most extreme temperatures. These points, called the hot poles, face the Sun when Mercury is at perihelion, receiving maximum solar radiation. At these locations, the temperature can reach nearly 900 degrees Fahrenheit. Meanwhile, points located 90 degrees away in longitude, called the cold poles, face the Sun when Mercury is at aphelion and experience somewhat cooler maximum temperatures. The combination of Mercury's slow rotation and eccentric orbit creates bizarre effects for a hypothetical observer standing on the surface. From certain locations, you would see the Sun rise, stop, move backward across the sky, stop again, and then continue forward before setting. This happens because Mercury's orbital speed varies according to Kepler's laws. When Mercury is closest to the Sun, it moves faster in its orbit, and this increased orbital motion can temporarily exceed the rate of the planet's rotation, causing the Sun to appear to move backward. Another consequence of the 3-to-2 resonance is that different parts of Mercury's surface experience dramatically different numbers of sunrises. If you stood at one of the hot poles and watched for 2 Mercury years, you would see just 1 sunrise and 1 sunset. Meanwhile, standing at certain other longitudes, you would see the Sun rise, reverse course and set, then rise again and set again, all during the same Mercury day. Scientists believe Mercury's unusual rotation rate is a result of tidal forces from the Sun acting on the planet over billions of years. Just as Earth's gravity raised tides on Mercury and gradually slowed its rotation, the Sun's gravity acted on slight asymmetries in Mercury's mass distribution, eventually locking the planet into its current 3-to-2 resonance. This process, called tidal despinning, affects all planets and moons, though the final state depends on the specific characteristics of each body. Mercury's orbit also precesses, meaning the orientation of the orbit slowly rotates over time. This precession occurs for all planets due to the gravitational influence of other planets, but Mercury's precession includes an extra component that could only be explained by Einstein's general theory of relativity. This small but measurable effect made Mercury crucial in confirming one of the most important theories in modern physics. One of the most surprising discoveries about Mercury came in the early 1990s when astronomers using Earth-based radar detected bright, radar-reflective patches at Mercury's north and south poles. These patches had characteristics consistent with water ice, a discovery that seemed absurd given that Mercury is the closest planet to the Sun. How could ice exist on a world where daytime temperatures can melt lead? The answer lies in Mercury's unusual orientation and the permanent shadows that exist in deep craters near the poles. Mercury's rotational axis is nearly perpendicular to its orbital plane, tilted by only about 2 degrees. Earth, by contrast, has an axial tilt of 23.5 degrees, which gives us our seasons. Mercury's minimal tilt means that the Sun always stays close to the horizon at the polar regions, and the floors of deep craters never receive direct sunlight. These permanently shadowed regions act as cold traps, where temperatures remain cold enough to preserve water ice for billions of years. Even though Mercury's equator bakes under intense solar radiation, the poles stay in eternal darkness, maintaining temperatures as low as -370 degrees Fahrenheit. This is cold enough to freeze carbon dioxide, not just water. The evidence for water ice at Mercury's poles became even stronger when NASA's Messenger spacecraft orbited Mercury from 2011 to 2015. MESSENGER's neutron spectrometer detected elevated hydrogen concentrations in the polar regions, consistent with water ice. The spacecraft's laser altimeter measured the reflectance of the polar deposits, finding they matched the properties of water ice mixed with a darker material, possibly organic compounds. Scientists estimate there may be between 100 billion and 1 trillion metric tons of water ice in Mercury's polar regions. That sounds like an enormous amount, and in absolute terms it is, but it's concentrated in areas of permanent shadow within craters. Some of this ice may be relatively pure, particularly in the coldest areas, while other deposits appear to be covered by or mixed with darker material that may be organic-rich compounds. Where did this ice come from? The most likely sources are comets and asteroids that have struck Mercury over billions of years. Comets are essentially dirty snowballs, containing significant amounts of water ice along with dust and organic compounds. When a comet impacts Mercury, most of the water vaporizes in the intense heat of the impact and is lost to space. However, some water molecules bounce around the surface until they eventually migrate to the permanently shadowed polar regions, where they freeze and accumulate. Micrometeorites also continuously deliver small amounts of water to Mercury. Though each micrometeorite carries only a tiny amount of water, over billions of years, these impacts add up. Some scientists have also proposed that chemical reactions between hydrogen from the solar wind and oxygen-bearing minerals on Mercury's surface could produce water molecules, though this is likely a minor source compared to cometary delivery. The discovery of ice on Mercury has important implications beyond understanding this one planet. It tells us that even in the most unlikely places, water can find refuges where it persists. Similar cold traps exist at the lunar poles, and indeed, ice has also been detected on our moon. This is important for future space exploration because water is a precious resource. It can be broken down into hydrogen and oxygen, providing fuel and breathable air, and of course it's essential for human consumption. Mercury's ice also preserves a record of the solar system's history. The water molecules frozen in those permanently shadowed craters have been locked away for potentially billions of years, protected from the sun's radiation and heat. Studying these ancient ices could tell us about the composition of early comets and asteroids, the history of water delivery in the inner solar system, and even provide clues about the ingredients that made Earth's oceans. Sending spacecraft to Mercury is one of the most challenging endeavors in space exploration. The planet's proximity to the Sun creates intense thermal and radiation environments that can damage spacecraft systems. Additionally, reaching Mercury requires tremendous amounts of energy. Counterintuitively, it's actually harder to send a spacecraft to Mercury than to send one to Mars, even though Mercury is closer to Earth. This is because of the Sun's immense gravitational pull. When a spacecraft leaves Earth, it's already moving around the Sun at Earth's orbital speed of about 67,000 miles per hour. To reach Mercury, which orbits much closer to the Sun, the spacecraft must lose a tremendous amount of this orbital energy. It's like trying to slow down a speeding car, requiring enormous amounts of fuel or clever orbital mechanics using planetary flybys. The first spacecraft to visit Mercury was NASA's Mariner 10, which made 3 flybys of the planet in 1974 and 1975. Mariner 10 discovered Mercury's magnetic field, took the first close-up images of the surface, and measured the planet's basic physical properties. The spacecraft used a gravity assist from Venus to help it reach Mercury, pioneering a technique now commonly used for deep space missions. During its 3 encounters, Mariner 10 mapped about 45% of Mercury's surface at resolutions far better than any Earth-based telescope could achieve. However, after Mariner 10, Mercury remained unvisited for more than 3 decades. The technical challenges and high costs of a Mercury mission meant other targets received priority. This changed in 2004 when NASA launched the Messenger spacecraft, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging. Messenger took a complex route to Mercury, performing 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys before finally entering orbit around the planet in March 2011. Messenger spent 4 years orbiting Mercury, revolutionizing our understanding of the planet. The spacecraft carried 7 scientific instruments that studied Mercury's surface composition, mapped the planet's magnetic field, measured the exosphere, and took thousands of high-resolution images. Messenger confirmed the presence of water ice at the poles, discovered that Mercury's surface contained surprisingly high amounts of volatile elements like sulfur, and found evidence for relatively recent volcanic activity. One of Messenger's most important contributions was completing a global map of Mercury's surface. For the first time, scientists could see the entire planet in detail, not just the 45% mapped by Mariner 10. These images revealed additional huge impact basins, extensive volcanic plains, and numerous examples of the planet's unusual tectonic features. The spacecraft also discovered that Mercury's magnetic field is offset from the planet's center, shifted northward by about 300 miles, a peculiarity that scientists are still working to explain. Messenger's mission ended in April 2015 when the spacecraft, having exhausted its fuel, was deliberately crashed into Mercury's surface at over 8,000 miles per hour. The impact created a new crater about 50 feet across, adding one final mark to the planet Messenger had studied so thoroughly. This controlled crash was carefully planned to occur on the far side of Mercury, where it wouldn't damage any scientifically interesting regions. The next mission to Mercury is Baby Colombo, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, launched in 2018. Baby Colombo consists of 2 spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, which will separate upon arrival and study Mercury from different perspectives. The mission is taking a long route to Mercury, using gravity assists from Earth, Venus, and Mercury itself to gradually adjust its trajectory. Baby Colombo is scheduled to enter orbit around Mercury in 2025, where it will study the planet for at least 1 year, with possible extensions. The mission carries a suite of instruments designed to build on Messenger's discoveries, including high-resolution cameras, spectrometers to study surface composition, magnetometers to map the magnetic field in detail, and instruments to study the exosphere and magnetosphere. Mercury formed 4.5 billion years ago from the same disk of gas and dust that gave birth to the Sun and all the other planets. In the early solar system, the region close to the Sun was extremely hot enough that only materials with high melting points, like metals and rocky minerals, could remain solid. Lighter, more volatile materials like water ice and organic compounds were vaporized by the intense heat and pushed outward by solar radiation and the solar wind, which is why the inner planets, Mercury, Venus, Earth, and Mars, are all rocky while the outer planets are gas and ice giants. Small particles of metal and rock in the inner solar system began sticking together through collisions, gradually building up larger and larger bodies called planetesimals. These planetesimals, ranging from miles to hundreds of miles across, continued colliding and merging in a violent process called accretion. Over millions of years, a few dominant bodies emerged, sweeping up most of the material in their orbital zones and becoming the terrestrial planets we know today. The early solar system was a chaotic place, with planetary embryos and leftover planetesimals careening through space on intersecting orbits. Mercury likely suffered numerous giant impacts during this period, collisions energetic enough to melt the entire planet and perhaps strip away portions of its mantle, which might explain its unusually large iron core. Some scientists think Mercury might have originally formed farther from the Sun and later migrated inward due to gravitational interactions with other planets and the protoplanetary disk. Once Mercury reached approximately its current size, the planet began to cool. The interior was initially molten throughout, but over millions of years, heat radiated away into space, and the planet began to solidify from the outside in. As the interior cooled and contracted, Mercury's crust cracked and formed the giant scarps we see today. Volcanic activity, powered by heat from the interior and radioactive decay, continued for billions of years, creating the smooth plains that cover much of the surface. About 3.8 billion years ago, the inner solar system experienced a period called the Late Heavy Bombardment, when a sudden increase in asteroid and comet impacts pummeled the terrestrial planets and their moons. Evidence for this bombardment is preserved in the heavily cratered surfaces of the Moon, Mars, and Mercury. The Caloris Basin and other large impact structures on Mercury likely formed during this violent period. After the late heavy bombardment ended, impact rates decreased to roughly their current levels, and Mercury's volcanic activity gradually ceased as the planet's interior continued to cool. For the past 3 billion years or so, Mercury's surface has been relatively stable, modified primarily by occasional impacts and the slow contraction of the planet as its interior continues to cool. The small scarps that cut through relatively young craters tell us that this contraction is still happening today, making Mercury one of the few tectonically active terrestrial bodies in the solar system. What does the future hold for Mercury? For billions of years to come, Mercury will continue orbiting the Sun much as it does now. The planet will continue to slowly cool and contract. Its core will gradually solidify, eventually shutting down the magnetic field. The exosphere will continue its endless cycle of loss and replenishment. Micrometeorites will keep grinding the surface into ever finer dust. The ice-hidden and permanently shadowed craters will remain frozen, a cold archive in a scorched world. In the very distant future, about 5 billion years from now, the Sun will exhaust its hydrogen fuel and begin fusing helium, expanding into a red giant. As the Sun swells, it will likely engulf Mercury entirely, vaporizing the planet that spent its existence closest to our star. But that fate lies so far in the future that the time span is almost meaningless on human scales. For now, Mercury continues its eternal dance, a small gray world circling our Sun, keeping secrets in its iron heart and ice-filled craters, a reminder that even the most familiar neighborhood, our solar system, still holds mysteries waiting to be understood. And on that note, we've completed our journey through Mercury, from its ancient discovery to its distant future, from its scorching surface to its frozen poles, from its enormous iron core to its wispy exosphere. This small planet, so often overlooked in favor of more dramatic worlds, reveals itself to be a place of extremes and surprises, a natural laboratory where we can study planetary processes pushed to their limits. Thank you for joining me on this voyage through the innermost realm of our solar system. I hope you found it as fascinating as I have. Until next time, keep looking up, and may your dreams be filled with stars.